Okay, so off we go. Here's where we left off last time. So first of all, welcome back, everybody. I hope everybody had a good, relaxing break. Triple integrals. This is going to be a lot like double integrals. It's just that instead of taking a two-dimensional region and slicing that up into little pieces on which to answer questions, we're going to be slicing up a three-dimensional region. So, for example, if you want to know how much mass there is in some sort of a three-dimensional region, instead of how much mass is distributed over a two-dimensional region, that's the kind of question we're going to be interested in. So, for example, here's a solid three-dimensional region, box. We're going to start off with just a box because just get the ball rolling. This is kind of the easiest first example. If you're interested in how much mass is in this box, mass is an accumulating quantity. The whole is the sum of the parts. So chop it up into little pieces, add up the masses on those little pieces. It's the basic big picture strategy. Now, on each little piece, how would I compute how much mass is in each one of these little pieces? Well, I have this idea of mass per unit volume. Let me see if I can squeeze. Oh, and let me go full screen. There we go. That helps. On each little piece, I can talk about mass per unit volume times volume. Right? That's how we compute mass on some little piece. Just like we did with double integrals, frankly, except for double integrals, the mass was distributed across area instead of volume. And so it was mass per unit area times area. Okay. All right. So on each little piece, the question is simple, and then I just want to talk about how to add that up over all of the pieces. And then again, the whole is the sum of the parts. So there's a bunch of little details you have to worry about here. We're going to add up, but we're going to add up in three different directions, right? There's sort of in the x direction, in the y direction, and in the z direction. So there are three parameters, three indices down here, I, j, and k. Right? So in some sense, that's a three-dimensional summation, you might say. There's new little particulars about what happens when I slice up the z-axis. No big deal. This is all highly analogous to when we sliced up the x-axis and when we sliced up the y-axis. Different particulars. So a couple little extra details, but basically chop it up, add it up. This is what we're adding up, and this is how you add them up, pretty much. Okay, so this is a strategy for computing the answers to a large category of questions, and as such, it deserves a name and a notation. This is what we're going to call a triple integral. This right here, this 3-index Riemann sum is a triple integral, and the notation that we use to represent that is this. So just to emphasize, this thing on the left here, that's just a convenient shorthand notation. Right? This is what a triple integral actually is. Everybody happy? Okay. Yes?
What's the R on the lower boundary?
Yeah, so this little r here is, that's the name that I've given to whatever my domain is. In this case, my domain is a box, right? And I'm using that times-looking notation. It's analogous to a similar notation for two dimensions. Yeah. Okay. All righty. So now again, good news. Just like with double integrals, there's different levels of formality that you can go to in defining all of this stuff, and the book, spends a little time talking about a little bit more rigorous presentation of these ideas, and there's good reasons for it, and it's important in other contexts. In Math219, it doesn't affect us at all, so you're not responsible for any of that stuff about irregular partitions or test points, because we're going to focus on continuous integrands where none of that makes any difference at all. Okay. All righty. So now, just as a quickie example, and hardly anything happens in this example that we haven't already talked about, but if you want to compute the total amount of mass of whatever in some three-dimensional box, well, as we've already discussed, the whole is the sum of the parts. That's all this says here. It says I'm taking my solid, I'm chopping it up, and, dicing, I guess, it up into little teeny tiny little sub boxes, each of which has a little bitty mass, all of which I'm going to add up. And then on any little piece, as we've previously discussed, the amount of mass in a little piece is mass per unit volume times volume. How are we doing? Is everybody on board? All right. Okay. Here's a warning before we get into the examples and further developments. How do we visualize this? And this, again, kind of a little landmine here, and I want to make sure everybody sees the landmine so you don't step on it. I'm going to start with a reminder of single variable calculus, and here's how everyone gets single variable integrals presented to them for the very first time. The question is phrased, all exceptions granted, most people see it as phrased as, how do we compute the area under a graph? Right, area under a curve, but specifically a graph. Okay, that's fine. It's true statement, but y'all will recall that it's not my favorite point of view. Now that said, I missed the thing. Let me try that again. There is a kind of analogous point of view about double integrals. You can think of double integrals as computing the volume under a surface. And I even started with that, again, just to kind of make the easiest sort of connection to the single variable. So it looks analogous, so things kind of seem like they're in order. Fine. Okay. Now, my preferred way to think about these things, and I'll explain why, I'll remind you why in just a minute, is to think of them without resorting to graphs. Because in whatever application you might be looking at, there may be no reason to even think about a graph. And so why invent something that's not necessary? Right? So for example, you may have mass distributed across an interval on the x-axis. They like to talk about the mass of a non-constant density rod as a way of saying this. And well, you can break it up into little pieces, and on each little piece, mass per unit length times length tells you how much mass is in each piece, and then you add up. So one way to think about a single variable integral is that you're adding up little pieces of mass on the x-axis. Likewise with a double integral. You can think of it as maybe we have mass distributed across a two-dimensional region, and on each little piece, how much mass is in any given little piece? Well, mass per unit area times area. Right? And so that gives you a way to visualize, or a metaphor for double integrals. All right. So two competing ways of visualizing, what integrals are. Now here's where things get weird. Let's think about these points of view here real quick. One-dimensional integral, we understand with a two-dimensional picture. Two-dimensional integral, we understand with a three-dimensional picture. This is a kind of a disturbing little pattern we've got here. Can I extend this to making sense out of a three-dimensional integral? Well, if I can understand four-dimensional pictures, I can, but I can't. Right? And I don't think you can either. Right? So this is a second reason why I would say I'm cool on this idea of understanding integrals in terms of graphs. Not only is it sort of unnecessarily narrow in its application, it's unsustainable. If you want to be able to make sense out of triple integrals, this point of view is a dead end. You can't, again, unless you're got some superhuman ability to visualize in 4 dimensions that I certainly don't have, there is no way to extend this. Everybody see the problem? It's a nasty, nasty little problem. So now on the other hand, reminder, I like to think about integrals from the mass point of view, and let's count dimensions. Well, a one-dimensional integral, one-dimensional picture. Two-dimensional integral, two-dimensional picture. I like this pattern. So how do I make sense out of a three-dimensional integral? Hey, no problem. We can draw a three-dimensional picture. So this is a perfectly sustainable, okay, I guess it's artistically a little bit challenging, to draw three-dimensional pictures and to visualize three-dimensional solids. Fine. But it's perfectly accessible. Maybe a little tricky. How we doing? Everybody happy? Okay. All right. Okay. Let's see here. So here's a question that I get a lot from students, and I'm going to anticipate the question so that y'all don't have to ask it. So the question I get from students a lot is, how come sometimes a volume is a double integral and sometimes it's a triple integral? How do I know? Aren't we doing the same thing with two different constructions, and why, and what's the point? Why do we even need triple integrals if you can understand volumes with two-dimensional double integrals, and what's going on here, right? And of course the answer to this confusion is to just realize this is an apples and oranges comparison, right? So this student's not doing a good job of dividing, keeping a clear division between one sort of pattern of metaphors, pattern of applications of integrals, versus a different pattern of applications. Right? And we're apples and oranges. Yeah?
So can we almost think of the right side as a projection of the structure on the left side there?
Yeah, but kind of, in a way. Yeah. There's a point of view there that, this is like the footprint. Yeah, totally. And now what's nice, I'm full conceding, right? It is nice to be able to have a dimension to represent what the integrand is, and it's cool that you can do that in this context. And I confess that is kind of hidden in this picture, right? There is an F, but I don't see the F, and so you kind of have to let your imagination do that for you. Yeah, but yeah, totally. It's this is basically a footprint of that, and where the integrand is that's represented in that picture is just invisible in this picture. Sure. Yeah. Okay. So anyway, make sure to when you're thinking about various different kinds of integrals and you're trying to visualize what does this look like. Again, keep in mind there's this massive difference between this red category of pictures and this green category of pictures, and don't conflate these different things. Okay. All right. Okay, moving along. Yeah. So let me come down to this diagram. Y'all probably recognize this diagram, and I'll scroll back up in just a second here. This is a shameless ripoff of the diagram that I made for double integrals, kind of our strategic diagram of what connects to what, and by way of reasonable arguments, and what isn't a reasonable argument. And you'll notice some differences. So the first difference that you're going to notice is that this doesn't even have a name right here. This is what volume was when we were talking about double integrals. This is how much stuff is under the graph of whatever your integrand is. And of course, that's a four-dimensional thing when you're talking about triple integrals. So we can't make any sense out of that. It's just, this is a non-starter. At least in a class like Math219, we can't make any sense out of that. And by the way, side note, it can be done. It's not unreasonable. It's just not what this course is about, so not our problem. Naturally, then, for even more reasons, you can't directly argue that mass is this incomprehensible four-dimensional thing, because if you don't understand the thing you're claiming it's equal to, how can that be an argument, right? So that's obviously nonsense. Now, other gap, missing thing on there. I can't argue that I can compute this thing in two different ways to therefore conclude that these two things are equal, because I can't compute it anyways because I don't even know what this is, right? So again, dead in the water. I can't make that argument either. Here's the good news. Good news is even though I can't make that argument, it does remain that triple integrals can be computed with iterated integrals. This is still true. Now, how do you know it's true? You know, what argument can I give you to persuade you that this is true? Not much of an argument can I really give you in this class. There is a perfectly reasonable algebraic argument that results in this conclusion. And in my opinion, it's not a good investment of time in this class. It's, I think, really above this class to be done properly. And so I don't think it's a good investment of time for us to do that. So I'm just going to assert that this is true. You can find this theorem in the book, and I'm just going to suggest that we just accept that this is true. Is that cool? Everybody willing to believe this? You'll notice how analogous this is to the double integral result. Yeah.
So I noticed you wrote it in two variations, but there's obviously a third.
Yeah, ... There's 6 of them actually.
Oh, okay.
Yeah, because there's 6 different ways to order
right.
3 things, and you know.
And they all work.
They're all the same. That's right. Exactly. Okay, so that's a little bit of good news. Again, I can't justify it. The justification would require 4-dimensional nonsense or tedious algebra that we don't want to mess with, but that does still work. And we've already argued that, for example, mass can be written as a triple integral. Oh, yeah, question.
Is switching the order like that only for like a cube?
Yeah, that's right. That's only for rectangular boxes. Can you switch in all 6 different possible ways? That's right. That's right. And we're going to talk about non-rectangular domains momentarily. Yeah. Okay, so we can still argue that applications, like we already did it with mass, that the whole is the sum of the parts and stuff like that, and we can write down triple integrals. And we've now, I'll say, accepted, I hope, that triple integrals can be written as iterated integrals, and hopefully no surprise, iterated integrals you can always crank out, starting on the inside and working toward the outside. You can have to do 3 of them instead of 2 of them because it's a triple integral instead of a double integral, but nevertheless you can crank and get an answer. So we actually have a strategy which is like so, right? Like I have in yellow there. That is our strategy for how we're going to answer application questions. Is that cool? Okay. All right. Okay. So let's do one. Let's see how to shrink that. There we go. Let's see here. We were asked here to compute the mass. Oh, whoopsie, that's too big. We're supposed to compute the mass in a rectangular box where mass per unit volume is given by that expression right there. Fine. Okay, well, first, the mass is a triple integral of density. We've already made that argument. That was our first example. Whole is the sum of the parts, et cetera, et cetera. We just claimed, and I'm going to cite here, that you can rewrite triple integrals as iterated integrals. Right? Citing that theorem. And then all that remains is the cranking, actually doing the fundamental theorem here and actually evaluating this iterated integral. It is very much like double integrals. So let me just hit some highlights here. Let's look at this inside integral. That inside integral is what we're doing here. And now it is tempting to look at this term and to get worried and think, oh my gosh, look at all those variables, and there's a product of 3 factors, and I wonder if I could do integration by parts or something like that. But nope, this is not a product of 3 separate non-trivial factors. There's a lot of constants in there. Right? And what you got to remember is that variables further to the outside are constants, and as such we treat them as constants. So that xy right there, that's a constant. And what we're actually dealing with in terms of integrating this term, we're actually dealing with just a 2z and doing an integral with respect to z, which is just z squared. Does that make sense to everybody? Okay. And then, yeah, a constant is a multiplicative constant, and it comes along for the ride. That xy is still there. Yeah, sure. But the meat of the matter is just integrating 2z to get z squared. So again, you've got to always keep track. At every stage in this calculation, constantly remind yourself of, wait a minute, which integral am I doing? Which variables are further to the outside and are therefore constants? And then capitalize on that wonderful convenience. Okay. All right. All right, and the rest is a bunch of details. Y'all can make your way through the rest of that. And again, please do make sure to do that. I'm going to assume that everybody's proficient with the execution on computing iterated intervals. Yeah.
Is R always like given in terms of x and then y and then z?
Oh, well, now this notation where I use the sort of times, yeah, that is always, this is the first variable, and this is the second variable, and this is the third variable. Now, what are those variables? Well, that depends on the setup of the question. But if the variables are x, y, and z, well, look at this, and conveniently in this case, they're listed with x first, y second, z third. So,
okay.
So there's the giveaway. Yeah. But do always keep in mind sometimes your variables aren't x, y, and z. Sometimes it's p, q, and I. Right? Or sometimes it's x1, x2, and x3. So you got to interpret accordingly. Yeah. Alrighty. Okay. So what about non-rectangular domains? And here is where I'm again going to have to ask for a little bit of faith. So real quick, I'm going to go back a few pages, back to when we were talking about double integrals. Right? Here's how we argued non-rectangular domains for double integrals. And we were able to draw this picture where we can see and get satisfaction from seeing what our slices look like and what we're doing with them, right? And we're multiplying the area times the thickness and all that business, right? And the punchline, though, was that what you're really doing only involves the domain, and on the domain, we pick a direction in which to do our slicing. We talk about what a slice looks like, make sure we have a clear idea of what in this case, a Y slice looks like. A Y slice is perpendicular to the Y-axis. And we talk about where they start and where they end. Now, Y starts at that slice where Y is C and ends at that slice where Y is D. Right? And then, having found those bounds for the outer integral, I then fix a value of y, focus my attention on that slice, now look in the next direction. My next direction is the x direction. Here's where I start, that gives me my lower bound. Here's where I end, that gives me my upper bound. And at that point, we're done. Now, in some sense, we only had to go through what I'll call the process here twice. Now that we're looking at triple integrals, we're going to basically have to go through this process 3 times, but it's going to be morally the same process. So here we go. So, here we go, and it's a tough little bit of art to draw. So we'll start off. Oh, and by the way, on this first example that I'm doing, for no particular reason, I'm going to put my differentials in this order. Again, you got a total of 6 options, and so take your pick. And for the purposes of what we're doing here, it really doesn't matter. I just thought I'd keep them in order to make it kind of a little bit easier to keep track of what's going on for this very first example. Okay. All right, so with that in mind, we're doing our X slicing first. Here's going to be our process. We're going to slice perpendicular to the first variable's axis. So we'll be slicing perpendicular to the x-axis. Perpendicular to the x-axis looks like that. Our slice looks like this. Now that's a two-dimensional surface instead of a one-dimensional curve. So everything's one dimension up, right? But nevertheless analogous. So that's what our slices look like. Next, we have to ask what's the range of values of x. So looking at these slices, I ask where is my first slice? We're going to look at the first slice. Okay, my first slice of this sort. Now, geometric appeal, you've got to see it from the picture. Thinking about these slices perpendicular to the x-axis, the very first one is whatever is the sort of the backmost point on this lump of a solid. And that is going to determine, that's going to determine our starting value of x. And then our very last slice, let's see here, I'll do this in purple. Our last slice, well, again, you got to rely on the picture here. I'm thinking about these x slices perpendicular to the x-axis. The very last one is going to be at whatever this frontmost point is. And that will give us our x2. This is just one dimension higher, but totally analogous to what we did with double integrals. Everybody see that? Okay, now, just like we did with double integrals, we are now going to fix a slice. So I'm going to fix a value of x. We're going to focus our attention now just on this one x slice. And on that x slice, we go back up to the top. And we now ask, okay, and let me do this with a pen. How about that? What happens as I slice now perpendicular to the next axis? And you may recall that our next axis is the y-axis in the way that I had it set up arbitrarily. So again, we got to think about what do slices look like? Where's the first one? Where's the last one? Okay, now let's start. Okay, what do these slices look like? This is artistically hard. Here's my attempt at drawing a slice perpendicular to the y-axis. Again, I just have to make a geometric appeal here. You got to think about use the picture to think about visualizing this solid thing. And I've got this x slice that I've already taken. What happens now when I take this x slice and now slice like this perpendicular to the y-axis? So I have sliced perpendicular to the x-axis. Now I'm going to slice perpendicular to the y-axis. And my geometric appeal is that I will get a little line segment like that. Y'all buy it? And you get various, for different values of y, you'll get these various different line segment things about like this. Everybody good? All right, so we got to think about first and last. Whoops. Oh gosh. Okay, first and last. Okay, so the very first of these slices is going to be whatever that leftmost point is. The particulars of the geometry will tell us how to find what that point is. And we'll talk about those particulars when we get into an actual example. But we're going to have to figure out from the picture where is that first slice. And that will give me my starting value of y. Excuse me. And then we got to figure out where it is that last slice, and that will give me my ending value of y. Let me make this a little bit bigger. Oof. There we go. How we doing? Now let's think about what these bounds are going to be. Let's talk about y1 and y2. Is y1 going to just be some number like 4? Probably not. It depends on x, right? I mean, you look at this picture here. I've got some x slice picked, and this is what the slice looks like for that value of x. But I mean, look, if you take a different value of x, you're going to get a totally different slice. That totally different slice might have a different lower bound for y and a different upper bound for y. So these y1 and y2 will vary depending on what x is, or said differently, they are functions of x. And so I think that's an important thing to sort of make note of. The inner bounds, just like with double integrals, the inner bounds are functions of the outer variable. Everybody on board? And you can see that in our developed integral here, that, let's see here, y1 and y2 are functions of x. Hang on. Okay, so this is the integral we're looking at, and they are functions of the outer, in this case only x, the outer variable. Okay. All right, and then proceeding along, and oh gosh, let me come up here and clean up my mess. Reminding ourselves of this process. We sliced orthogonal to the y-axis. We found the bounds for the y integral. Now we have to fix a y slice, keeping in mind that we've already fixed x. So we're going to be looking at fixing a particular y slice of our particular x slice. And let's draw that picture. We've already decided to fix x, to give me that. And then we're going to fix y to give me, that. And here's another way to say it. Different point of view on the same thing. Having fixed both x and y, I'm basically designating a point down here in the xy plane. This is all that remains. And now I have to imagine, how then does z vary as I move along this y slice of my x slice? So slicing perpendicular to the z-axis, let's see, I will have a starting value of z that'll come from, well, again, wherever the first point is. It's going to depend on both x and y. Because again, you can see in the picture, this bottom point depends on what is this x comma y down here above which I'm looking at that as being the bottom point. Different x's and y's moving around down here in the domain. I'm going to get different little line segments in green and a different lower bound point in purple, and therefore a different z coordinate. Everybody see that? Yep.
Yeah, sorry. I had a question on why we have the y values only depending on x. What if the points you get for the first and last values of y are the same z height?
The z heights are just not relevant to what we're asking at that point, right? Yeah. So I mean, we'll get to them, right? And so, for example, if you think about, let's look at this point down here in the xy plane, right? That little point in the x. So for that value of x and whatever that value of y is, then okay, yeah, for that x and that y, then our little, our slice in the z direction is just a point, right? So yeah, we'll get to it, right? It's just that we get to it for sort of extreme values of x and y.
Okay.
Is
But
that
not
cool?
just for y.
I'm sorry?
But not just for y.
That's right. It's for x and y. That's right. Yep. Yep. All right. Okay. Yeah.
But what if y was like a function of x and z?
I don't understand.
Like in this case, we're assuming that we're given the initial and final x, and then based on that, y is a function of x, so you find those points for the slices of y.
Oh, well, that's because I made this arbitrary choice to put my differentials in this order.
Oh, I see. So if you get into
Yeah, if you change these differentials to change the order of your slicing, then yeah, everything changes. So this is just an example, right? And there's 5 more sort of equivalent pictures that one would have to draw, which I think you can see why I didn't want to, right? So yeah, this is just a for example. So try not to think of this as x, y, and z. Think of this as the outside variable, the second variable, and then the inside variable. Yeah, totally. Yeah. Okay, so as I have indicated here, and analogous, corresponding to my picture, when we're looking at, let's say, the inside integral here, that inside integral is happening over this little part of the domain, and notice x and y are literally constant on that on those points of the domain. So I get to treat them as constants. X and y I treat as constants, or by the way, I think easier to remember, the variables further to the outside. Whichever variables are further to the outside, those are the ones that I've already fixed, and therefore those are the ones that I get to treat as constants in my integrand. And that's an important thing to keep in mind. Does everybody follow on that? And then likewise, our bounds, we've already talked about this, but I'll say it again. Our bounds for z, the lower bound, for example, that lower bound is going to depend on which point, what x and y. And so those bounds are going to be functions of x and y. And again, as it turns out, the inner bounds are allowed to be functions of the variables further to the outside. Everybody happy? All right. Okay, now a couple of little points of advice, I guess I'll call it. These are totally ripped off from the double integral discussion. We always construct the integral outside in. That's very important. As we just discussed, the bounds can be functions of the further to the outside variables, as we just discussed. And again, if you want to know what those bounds are, identify the relevant points on the picture. Got to have a picture. Those points are on certain geometric objects. With double integrals, it was curves. Now it's surfaces, because we're in space. Those surfaces will have certain equations, and then you just solve for whatever you need, whichever variable it is you want to find the corresponding bound of. Okay, so let's dive in and let's just see one. Now, in this first example, I am again going to make an arbitrary choice. No particular reason other than I'm going to follow the same pattern of the differentials here that we have in our generic diagram on the previous page. I just wanted to keep things analogous. Right, but again, there's 6 different ways that you can order these differentials, and they're all equally good in this particular case. And so, if you want to try to do this a different order, no problem. Probably a healthy exercise, in fact. Okay, so arbitrarily in this order, and now let's think about our x bounds. I got ahead of myself. Sorry. Let's think about our solid. Here's how our solid is defined. It's this tetrahedron. I've given you the 4 faces. By the way, there's a certain amount of geometric challenge there to look at those 4 equations and draw those 4 planes and think about, okay, what is that? Oh gosh, that bounds a solid. What is the solid that's bounded by those 4 planes? It's part of the problem, part of the question, right? So make sure that you are good enough with visualizing things in 3 dimensions and drawing things in 3 dimensions that you can actually persuade yourself that this is, in fact, what we're dealing with here. So that's just, there's no getting around the fact that this, the geometry of that sort is part of what this material is. It's you can't get around it. Okay. All right. Okay, so let's start with our dx slicing. Here's our x-axis. Keep in mind that slicing means we're making slices perpendicular to the axis in oh, that was a poor drawing. Let me do that again. There is a slice perpendicular to our axis. Again, we're looking at the x-axis to start. And one of those slices looks like this. Little triangle, like so. Everybody see the geometry there? Okay. Yeah.
So in the future, let's say like we're given a test question where we have to find something like this. Would we be given a graph of the object, or would we have to graph it out ourselves?
You got to draw the figure.
Okay.
Yeah, yourself.
So we should study these. Like,
you should
graph the tetrahedron looks like.
Yeah, that was going to be something I was going to say in a couple of minutes. But yeah, being able to draw, what I'm going to call mathematical drawing, 3-dimensional mathematical drawing, is actually pretty unavoidably important. So what you're going to notice, and you'll notice as we go through this example, that I'm going to refer to the diagram, and I'm going to say because picture, right? Thank you, picture. That the picture is what tells us in very many instances as we go along this process what it is that I need to look at. So yeah, being able to make a reasonable drawing is. It's really important for you personally, because otherwise you have to do the whole thing in your head, and that's really, 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 really hard, right? So obviously we don't want that. But it's also because you have to explain your thought process, right? Keep in mind, it's not about the answers, right? It's about the reasoning, and you've got to explain your mathematical reasoning. And how would you explain mathematical reasoning about geometry without a picture? That's a tough one, right? So it's de facto required that you draw reasonable figures representing what your mathematical reasoning was. Does that make sense?
Yeah.
Yeah. Okay. Yes.
But no matter what the picture looks like for that first variable is on the outside, that y and z, or whatever the variables are called, are going to be constants, right?
Say it one more time.
So like no matter the picture, y and z in the first equation are always going to be constants if x is on the outside.
You got ahead of me. You're talking about here?
Yeah.
Oh, yeah. We'll get to that.
Okay.
Yeah. Short answer, no.
Okay.
But I can see how it kind of looks that way. Yeah. No. Yeah. So we'll get to that in a couple seconds. Okay. So real quick, since I'm talking about drawing and stuff, right? And how drawing is again de facto required. In effect, it's just hard to avoid. Next natural question: how do I do that? What if I'm no good at drawing? How do I deal with what can I do if I'm no good at drawing? And the answer there is you just got to get good at drawing. Now, how do you get good at drawing? So I have carefully thought about everything that I have learned and sort of gravitated toward in the past 40 years of mathematical drawing, right? And everything that I know about how to do good mathematical drawing is in a series of videos that I put on my YouTube channel. And I think it's a pretty good series. It's about an hour or so of me talking about drawing. And again, everything that I know about mathematical drawing is in there. So step one, I think would be a good thing to watch those videos. They're in the miscellaneous topics playlist in my YouTube channel. The next thing, and again, unavoidably important, drawing requires chops. This is not knowledge, this is skill. And you've got to practice it. I I have the advantage of I've been doing it for 40 years, right? So that helps, right? But at the same time, it does, y'all can give yourself practice by, forcing yourself to actually, like maybe take figures that I have in my notes and try to reproduce them. That kind of thing, right? So give yourself plenty of practice and take it seriously. Okay. All right, so let's get this example done. So here is one of our slices. We got to think about first and last. So where is our first x slice? And I say it's this back here. What is the value of x for that first x slice? Yeah, it's a freebie. Look at it. It's right there. It's in the plane x equals 0. So how do I know what x is when x equals 0? Well, it's 0. It's just a freebie. So x equals 0, staring right at us. So you get lucky sometimes. That's a good thing. Totally fine. Now here's where it gets a little tricky. Again, that's what our x slices look like. Where is this last slice? That it's like a little sad little excuse for a triangle. It's just a point, right? And how do I figure out where this point is? Now, y'all probably can look at the geometry of this picture and just kind of see what it is. Again, the purpose of this example is not to get an answer. The purpose is to illustrate the process. So let's go through the process, however unnecessary that may seem. And that point is on what surfaces? Well, that's right. So one at a time. I can see it's on that surface right there. Thank you, picture, by the way. Couldn't figure that out without the picture. It's not obvious without the picture. You need the picture, right? So y equals 0 is the first one. Next, again, right from the picture, that surface, which is that. And then lastly, again, I conclude this from the picture. I see that plane right there contains the point I'm interested in. That has that equation. So if I'm interested in that point to find my upper bound for x, this is the algebra I need to solve. Reminder to myself, because I don't trust myself. I'm trying to solve for x because I'm looking for an x bound. Easy to mess that up and lose track and solve for the wrong thing, right? So solve for x. You get that, and that then is our upper bound. So bounds come from understanding points. Points are on certain surfaces. Surfaces have certain equations. Solve for what you're interested in. Answer. Everybody see the process? Okay. Let's look at the y bounds real quick, and I see that we're short on time. Fixing a value of x, therefore looking only at that value of x. Lower bound for y is going to, well, here's our y slices. The lower bound for y is, of course, obviously just that slice where, again, freebie. Y happens to equal to 0. You won't always get this lucky, right? I made a nice convenient starter example. Y equals 0 jumps right in the boat. And, the last y slice is going to be at that point, about which, again, I know 3 things. For one thing, I've already picked x. X is fixed. I like to write down x equals x. It's a silly tautological thing to write. It's arguably meaningless, right? This is my reminder that x is known. X is what it is, and that I don't need to do anything with it. What else do I know about this point? Well, picture tells all. I can see right there, right in the picture. It's on that face, which means z equals 0, and it is on that face, which means that. So again, see, the picture tells all. Right? Now again, what am I looking for? It's easy to lose track. I'm looking for a y bound. So in this algebra, I solve for y. Notice it's a function of x. It is allowed to be a function of x because x is further to the outside. And that upper bound for y is 1 minus x. Everybody see how this process works? So I'm going to let y'all think through that third bound. Here are the 3 different observations to make. Make sure you can get to that answer. Okay, see y'all later. Have a good rest of your Wednesday. Don't forget about attendance if I didn't already get you.